based brain for precision read netting in rangelands, from high-density detection to spatial core analysis that has been developed by Javier Martín Ferro and the supervision of Professor João Ricardo Pereira Alete. So now, first.
Thanks for introducing myself, and I will start with the presentation of the thesis. So I want to start with the fact that weeds are a really big problem. I'm not talking about the weeds that usually the police search. Rather than that, I'm talking about the plants that grow almost everywhere, not only in your garden and in the racelands, but also in between the bricks around your weed, for example. For those who don't know what I'm talking about plants such as the cardo that we have here in Spain, that are really common. But in other types of the world, in other parts of the world, we have other types of plants. For instance, the carrilla. In Hispanic America, the carrilla is a really funny plant, in my opinion, because it's basically a cardo, but it's up to 2 meters tall and up to 1 meter of width. And of course, it can cause some problems, especially because it grows really quickly. It can degrade the quality of the soil, which means a reduction in the productivity, not only cattle raising, but also in agriculture, which means, of course, an economic and ecological impact. So you could say, okay, it's a really big problem, we have a solution for it. Well, not really. The only solution that we have is to early monitor these type of infestations in order to prevent it with chemicals. However, because of the vast amount of terrain that we have to explore, especially in South America, it's really complicated to effectively detect and early monitor these type of weeds. But are there any solutions? Well, there might be, because with the emerging technologies such as rovers or especially drones, we are capable of exploring vast amounts of terrain in a really relatively cheap way, a really quick way. And using in the manufacture, we are capable of using the cameras to see where the drone is flying and effectively see and measure the density and try to monitor this type of infestations. It is true that because of the human factor, especially from farmers or the researchers that may work with this weed, there is an human error related with it. So if we were able to eliminate or reduce this type of error, it would be awesome, of course. So approaches that uses artificial intelligence, especially in the field of computer vision, they tend to work relatively well for this type of approaches, and they work really well. So if we were capable of developing a tool, not only a tool, but a model that is able to precisely detect this type of weeds and to create, on the other hand, a product that makes it easier to interact with the model and to obtain more information about it, or the frames or the imagery that we are obtaining from the drones, that would be awesome. Well, that's effectively the thesis topic that we are going to deal with, which is basically to develop that product and to train that model. So this is a complete engineering project. Starting an engineering project might be complicated, so we need to follow some methodologies. A really important one is the CRISP-ML, usually used when we have a product and a machine learning model. And from that, following these steps, we're capable of defining some objectives, which are to build a data set from scratch, to train, test, and evaluate our model, with an application in order to interact with the model that is capable of returning more data, not only the pure inference outputs, and to test the feasibility of the model strength in a simulated embedded system, because honestly that's the future. So we start with defining our problem that basically when we want to classify and detect something, especially a weed, we are talking about locating it. We are in computer vision, this is called the bounding box detection problem, and it's basically the challenge of locating this type of instances or objects in a frame. As you can see here, we have an example of the rangeland that we are talking about, and here we can see the boxes that we want to predict. These are effectively carriers. So we can use that using artificial neural networks. For those who don't know, they are basically a black box that, using mathematical operations and a little bit of algebra, we are capable of, while training them, we adapt some weights, and we are capable of, while giving an input, returning an output. Now, this pure architecture of the basic neural networks, they do not really work for our work. And we have to adapt it a little bit. We have to transform this architecture to the convolutional neural networks. Then, although the architecture remains a little bit the same, it is true that the operations, the mathematics behind it change. For example, we have some convolutional logics or some kernel operations that I'm not going to go into detail, but you basically have to know that the architecture remains the same, but the operations completely change. So, the problem with these convolutional networks, the previous architecture that I have here, is that although they work really well, they are kind of limited, not only in the inference time, they were really slow, but in terms of performance, they work well, but we were capable of achieving more. That's why YOLO dual loop ones appeared in the 2020, and it was a totally change of the paradigm because it changed a little bit the architecture using a backbone and a head, and it was capable of achieving much more better times of inference and achieving much more better time precision in terms of accuracy. And this is really important. We were capable of using different models in terms of size. So for those who don't know, when we are using a simulated system, it's interesting to measure the size of the model because we are using hardware, limited hardware, and that's relatively important. So this is going to be something important for our thesis. And here you can see the first YOLO architecture that, as you can see, is really similar to the one of the previous slide. So after that, I would like to comment a little bit metric because it's really hard to understand the work without understanding the metrics. So basically, a really important metric here is the intersection over the union, which is basically that formula. And we have some machine learning numeric metrics, the recall, the precision, and the F1 score. Now, these are relatively important, of course, but we are not really they are important. However, we also would like to understand and to have some really good values in the MIP. The MIP is dependent on the intersection over the union, and it's basically the average precision computed for all the predictions in those intervals, 50 or 50-95. And because of our business goal, that is basically to develop a model that is capable of measuring the density of the Cartilla in order to early monitor this type of problem, we also implemented the coverage metric, which is basically to sum up all the boxes that we were capable of predicting and dividing it between the area of the frame that we are doing the inference on. So after that, we can effectively start with the creation of our dataset. It was recorded by Amparo Quiñones, which is our associate researcher in Uruguay in the Palo Pique Research Station. Here you can see where it's located. And we used a drone for recording these videos. Here you have an example of the frame that we extracted. So, after having all this imagery, we have to effectively label it because this is the most crucial part to label the dataset. And we use an external tool such as RoboFlow because I personally consider one of the state-of-the-art tools for it, and it's a cloud-based solution that really helps a lot with labeling these images. And here we have an example of a labeled image, and here we have the bounding boxes that we define for the frame. These are cartillas. So, after labeling all this, it was really time consuming, up to 2 months doing this because it was hard. We had our first iteration of our dataset. As you can see, although we have nearly of 16,000 manually labeled instances of Cartilla, we only have 417 images. This, of course, is a limitation because the number of images is really limited because of the size of our dataset, and we have to fix that. Another problem is the current input size of the image, which is 1920 by 1080. And when we do training, what we do is basically to reduce the scale of the image. So if we have a bounding box that is really small, such as this example, and we resize it, we might lose the information. This is a problem because we can overfit our model or just add noise to it. So we have to fix it. How did we do it? We basically did some data augmentations that basically is to apply transformations for image transformation for our dataset. We did some flips, some rotations, and a random 2.5 blur, so we were able to increase the size of our dataset. And on the other hand, we used tiling methodologies. Tiling methodologies are basically to capture your image and divide it into sub-images. So what we do here, we were able of obtaining images of 640, 640 resolution, so we wouldn't be losing all that data. So after that, we have 2 final versions of our dataset. Both of them contain data augmentations, and we have the non-tiled dataset, which contains the tiled image resolution and the tiled The non-title one is still relatively limited, although we have improved the number of the data samples, and we have nearly 35,000 images of level instances of Cardinal. On the other hand, the type version, we have almost 11,000 images with an incredible number of almost 90,000 instances of cardinal labels. This is a really incredible big number, so we can be sure that we are not going to have any problem in terms of data limitations. So, after that, we are going to start with our experiments. We have to define some hyperparameters that I like to say. First, we are going to say that the models that we use here were the model, the yellow V8, 11, and 26 in the nano version, because it's the most lightweight version that we were capable of finding, and with a total training epochs of 200. So, for those who don't know what an epoch is one epoch is an entire iteration through your data set during the training steps. The batch size was 16 because of hardware limitation of my GPU. And we defined some seeds in order to assure some reproducibility and to average results in order to not have any possible outliers, because we did several trainings for the same model. The B-plus parameter is a really funny parameter that I found, and is directly related with the width of the box loss function in the proper loss function. And empirically, what we discovered is that the lower the value, the better the performance of the model. We have some hypotheses, but I am going to leave that for the questions part if you want to. And here you can see the training steps. On the left-hand side, we have the non-tight model, and on the right-hand side, we have the tight models. Here is the evolution of the MIP accuracy amongst the epochs, and as you can see, our models tend to perform fine correctly. Surprisingly, the non-tight models tend to converge at the 200 epochs, and they have nearly 80% of accuracy, whereas the tight models have a 90% of accuracy. We can be sure that there is going to be no overfitting because of the train validation loss, and this is really something surprising because we can see that the validation box loss, which is the box, is really hard to, it's not regular, the function is not regular because of what I previously said, the image resolution is really high, and this is going to have some problems. We can see that our model is not capable of doing this inference correctly. However, the type methodology effectively solves this. So this is, again, something that we wanted to fix. So, for the experiments evaluation, we can see that our models perform really well. And furthermore, well, here we have the rigor, precision F1 score, MIP50 and MIP5095, with some really good results, knowing that we have average data samples of 40 instances per image. But furthermore, we want to say that the coverage mean is really error is really small. So we can say that our model tends to, although it's not perfect in terms of precision, is really good in our business goal. Exactly. So after that, we want to develop the product. Is going to be a web solution that is going to help the researchers in the Colombian station to explore the information of the rangelands. So basically what we want to do is to detect the cartillas, to explore some weak density map, to have some web weak density map, and to obtain the real world coordinates from the predictions. We're going to use an architecture based on Docker, two independent Dockers, one for frontend, one for the backend. Nothing really fancy, just really useful in order to do some scalability if we wanted to. And here's the input. As you can see, we have the .pt model. The user can use the .pt model. The inference mode can be defined also as tiled or non-tiled. The user can also define the image that or video that wants to process. And there is a parameter called the density threshold. This is in order to generate some alerts if the density of the predicted image is going to be greater than this density threshold. So in order to be able to really monitor these types of fields. And here you can see the output. As you can see here, we have the density logs. So we can see in which seconds it was obtained, it was so that the density was greater than what we wanted. And here we can see an example of the predictions. These boxes, they are like candies. In in order to see that in the heat map, which is plotted with the real world coordinates, there is correlations, our mathematical operations for obtaining the real world coordinates effectively works and they perform really well. So after that, we want to optimize our model. Why? Why we want to optimize our model? Because what I previously said, we want to simulate an embedded system and see the performance of our model, if it will perform correctly there.
5 minutes.
Okay. So we are capable of reducing the latency. When you optimize the model, what you do is sacrifice a little bit of accuracy performance, and you gain it in reduce the latency of the model and the CPU or GPU usage. This means, in a drone approach, that you are going to be more time in the air, so you can explore a little bit more of the terrain. We are going to use NVIDIA CUDA and TensorRT for doing these optimizations. So, for the results, we can effectively see that comparing the standard Python, which are the non-optimized models, with the optimized models in 8 accuracy, the latency and the latency is reduced, and the frames per second, of course, increases. Now, if you see this, this is the type model. You can see that although the latency is reduced, the frames per second is really low. That's because of the overheat that we decided to divide the image for doing the inference. Because that's the input size. So what we do is to basically divide the input size, the input size into images, so that adds an overhead. And you can see also that although we have a little bit less of accuracy, our model is going to continue to perform well in most of cases. So, for following the CRISP methodology, we are capable of achieving all the objectives that we were capable of finding previously, to build a data set, to train the model, to deploy the product, and to test the feasibility of our models. Surprisingly enough, we were capable of having more future work that is currently being developed outside the scope of this thesis. Well, the next natural step is, of course, to integrate and test the model in a real embedded system, and to develop new approaches in semantic segmentation, which was not done because of data limitations and because it's more consuming than doing the labeling with bounding boxes. Improvements on the data set, because as I have previously said, the data size is relatively small when using non-annotations, and to increase the capabilities of the Carla UI. Why we want to increase the capability? Because it's been a tool that is being deployed on the Papa Pig Research Station. It's currently used by the researchers, and it works really well. And it works so well that we have presented a paper on the CAFE 2026. We are waiting for approval. We are currently writing another paper with more research not included in this thesis, of course. And my favorite is that we were capable of doing an open source contribution to the Contradictive repository, which is basically where the models, where are the global models, about defining a new secondary metric called the true positive MCA normalized error metric, which is useful for understanding the error deviation of the origin point of the box. So, any questions? Here you have some QRs. They are not going to have your phones. It's just in order so you can see some inference videos about the output. If you want to do it, that's fine. If you don't.
Alright, so thank you very much for your presentation. Also for sticking on time. So now we are entering the Q&A part. So,
yes, again, congratulations on your job, because I think it was very complete. The only thing is that I think that you try, or the grade is like more ambitious that you have the time to do. Because, for example, I see that you make the data generation with the row
Yes.
Then you work on the algorithm for the visual recognition.
Yes.
couple of paragraphs. I don't know if you plan on working on that in the future or if it's complete, because I feel like it's not explained enough.
In the thesis or in the presentation?
Both.
Well, it's complete. So what we do there is basically the algorithm that we have to do some transformation from the relative image. Sorry, from the image we will have the bounding boxes, which are the relative coordinates, right? So what we do is using some theorems from geometry and from real world. One of them is the flat Earth assumption, which I find it really funny. Is where you're of given the relative coordinates in that image, where you're of taking the real world coordinates using for instance, some hyperparameters obtained from the drone, such as, for example, the pitch, yaw, exactly, the altitude of the drone. Of course, one limitation that we have here is that we had to, the K-matrix that you have there in the thesis document, we didn't have it. Usually when you have it, your precisions, your transformation are going to be more correct, more precise, and we have to rebuild it from scratch, having some assumptions from the DigiDrone documentations. So of course we are going to have some errors about it with the real world coordinates, and I think that a really interesting next line work will be to try to improve that or to minimize the error even more. Because that's true that it's, although it works fine, there is an error. I think that it was estimated at 1.5 or 2 meters. I want to recall that it was that, but I'm not sure. But the error, although it's relatively small, of course, if we're looking for really precise transformation from relative coordinates to real world coordinates, it could be improved, that's true.
My question is more about the, you said that you calculate the coordinates, but for example, the UI never shows like a map or anything. I see that you calculate the density, and for that I know that you need those coordinates, but I don't see it, and since I think that the thesis was to locate these patches of plants to feed them, like to sanitize it. I don't know why you didn't explain more, like in the map or not, or you know.
Lack of time.
Okay.
Initially, this presentation was 50 slides, and I have to cut a little bit, but it was mainly because of lack of time.
Okay. And then another question that I have is because at first you talked about evolution networks and everything, and about the yellow model and everything, and then you said that you use Growflow to classify the image. I imagine that Growflow you pass it the videos as it?
No, it's later like this. So what we do is we have a video, we don't in the videos, right? We have some videos. And what we do was I have an script that process the video. So you can define a parameter that was an offset, and between those offsets, I put it on 3 seconds, you extract a frame. So what you do later is you upload it into RoboFlow, and RoboFlow what enables you is to label the image, to mark the boxes.
Okay. So
Yes.
you got the box.
I could have you upload directly the video, but I will have to pay,
Okay.
and I don't have fund for that.
Okay, that's okay. I didn't get what was Growflow. Okay. I think that's all the questions.
Right, so thank you very much and congratulations for reaching this point, also to your supervisor. I believe that the technical part is nice and it's interesting. I have just a couple of comments, mostly doubts, right? So one of the things is all the videos that you're using, they are not considering weather issues like, for example, fog or something, right?
Yeah, they are being considered. So, if you mind, I am going to.
I need to find any comment. That's why.
It is true. We have here defined the altitudes, and it is true that's an error by myself because I didn't include all of these videos are in sunny weather, except these 2 ones that were recorded when in a cloudy environment.
Right. All right. So, all right. So there's no cloudy.
Sí,
All right. So there is no fog. There is no snow. There is no.
No, this is
No,
something that I talked with Amparo, and we have to think that in Uruguay the climate is differently from here. It remains really constant during the year,
Yeah.
and that's something that I didn't thought about it. And it's basically that it can be cloudy, it can be sunny, but you're not going to find snow in those parts. But what I wanted to do, and this is not included in the thesis, is that we read the data set, and now we have some videos from April and May. So we are trying to increase the seasonal variety.
Okay. Yeah. Okay.
But I mean, for labeling this data set, I spent 2 months because I had 16 manually labeled cartillas, and I could not be labeling each month, you know.
It's fine. But yeah. So there is something which is improper in your work, which is that you should have stated, okay, it will only work in up to now it only works in sunny weather, right? Or at least in
Yes.
it will not work if there is snow.
Yes, but something really important is that these models, of course, globally shifted. We cannot be assured that it's going to generalize correctly in the entire regions of Uruguay or Brazil or Argentina. It has been recorded in the press research station, so that's limited, that's for sure.
Okay. I will expect this to be stated clearly in the document, right? On the other hand, you have roughly 60% of training here. It's I would have appreciated to have lower amounts of training and see what happens, right? Because if I just look at your work in a very from bird's view on this,
Yes.
actually it's like, okay, I am doing object classification into videos, and then that's it, right? So I mean, afterwards you put a UI, and then you said that this is from a UAV, but from a technical viewpoint, this is just locating objects into videos, which are, by the way, it's not real as far as I remember, right? Right. So this is another limitation that actually it's rather weird, because nowadays we have a lot of use of APIs and real-time services. So what would you do if you had to do that?
And that's why I talk about testing the feasibility.
Yeah.
I bought a nanodesktop in Ori, which is the standard of the industry for doing, I don't have it here, but I have an image on a different version. It's the state of the art for doing inference on embedded systems in drones. So, of course, the next natural step will be to integrate and to develop an UAV that is capable of doing inference. It is true that although this DG drone is not capable of doing it, more expensive DG drones, you are capable of inserting your model into the drone, and it can do this type of inferences. But of course, we were limited because of the scope of the devices.
But the only thing that you need is actually a streaming from the drone, right?
You need to have, okay. Yes, of course, that would be a totally different approach. Yeah, I already do. We already the rest to explore.
Right. So that's it. Thank you very much. And let's move on to the next.
Yes.
Right.